Right. So let's take a look at some of these highlighted ones in your review document. Let's see. I want to move that. It'll be easier for me to read it on the screen. Number one. The force between two bodies have identical electric charges. If they have identical charges, right, or two negatives, either one, what kind of force are they're going to experience? We write it in physics, we write it like this. Repulsive forces, right? So A is your best answer there. And two. Atoms having equal or nearly equal electronegativities are expected to form what type of bond? Well, we can't say no bonds because it didn't tell us that one of them was, say, a noble gas. But if they have equal electronegativities, we should expect them to form covalent bonds. And if they're nearly equal, non-polar covalent bonds. So that's why C makes sense. How about number three? For elements cesium, fluorine, and chlorine. Cesium, fluorine, and chlorine. We want to order those in increasing electronegativity. Electronegativity, remember the trend. Over here, about like that, and then here, this. Then we have hydrogen here and helium here. So where's cesium? Cesium is way, way down here. Fluorine is way, way up here. Let's see. Yeah, fluorine is here. These are the noble gases right there. And then chlorine is right here. So if we want to increase electronegativity, we'll lower left, upper right. So that means in increasing electronegativity, it would be cesium, fluorine, then fluorine. That would be B. I'll leave that up here. We'll probably need it again later. Number four. The electron pair in a carbon-fluorine bond could be considered. All right, we have that. And remember, that line means two electrons. These are both non-metal, so this is going to be a covalent bond. Right? Should we expect it to be polar or non-polar? Well, the difference between carbon and fluorine is probably far enough away so that it'd be polar. Which means that, or something like that. So the electrons are going to spend most of their time, the probability scatter diagram would put them closer to the fluorine molecule. So closer to fluorine, because fluorine has higher electronegativity than carbon, that's B. And 5. Which of the following molecules has no dipole moment? Okay. And we've got carbon dioxide, ammonia, water, all in none. So we really need to look at these three. So you remember the Lewis dot structure for carbon dioxide. I mean, you can do it fresh if you want to, but it's carbon in the middle, double bond there, with lone pairs around the oxygen. This is completely non-polar, has no dipole moment. So it can't be this one, it can't be that one. So it has to be that one. Okay, by process of elimination. If we drew ammonia, it would have a hydrogen in the back. It would have hydrogens out here, right, forming that triangle base. Then you have a lone pair here. So its dipole moment would be like that. And water is even stronger. Water is a bent molecule. This is a trigonal pyramid. Water has two lone pairs here. So it's even a bigger dipole moment in that direction. Okay. This looks like I'm taking them in order for a little while anyway. Number 6. Which of the following has the smallest radius? Now we've got one neutral atom, and the rest of them are ions. Let me check something out here. Argon. What's the electronic structure for argon? It would be 18 here. It'd be 1s2, 2s2, 2p6. Then it'd be 3s2 and 3p6. See, that's 12, 14, it's 18. Okay, so that's argon. Let's look at these others. I have a sneaking suspicion. Potassium 1+ is 19 here, but it only has 18 electrons. And it's isoelectronic, right? So it's the same as argon. Chlorine. Chlorine is on the other side. So it has 17 protons, but it has 18 electrons, just like argon. So far we've got these are isoelectronic. Okay. Rubidium. No. Rubidium is going to be like krypton. So rubidium is going to be huge. It's going to be a lot bigger than any of these. It's going to be let's see. It would be like if we put argon in here, then what is it beyond argon? Well, beyond argon, we got 4s2, we got 3d10, and we got 4p6. That would be rubidium. Actually, rubidium +1, because it looks like krypton. So that's 37, that would be 36. This is 18 plus, 18 plus 18, 36. But it's not isoelectronic with these. Okay. And then the last one we have in here is sulfur. Sulfur is, well, I should have put sulfur down here. Well, we'll put it up here. Sulfur has 16 protons, and it's a 2- charge. So it has 18 electrons. It's isoelectronic. So we know, because this one has 3 Ds and 4 S's, it's going to be bigger than any of these. Right? We know it's the largest. So that won't be, the smallest radius wouldn't be this one. We need to look in here. What would be the smallest radius here? The one with the, since they have the same electronic structure, the one with the largest nuclear charge, the one with the most protons, would shrink it down. Potassium. Okay. All right, the more protons you have with the same number of electrons in the same electronic structure, it would be drawing those electrons down with that extra proton. So this is your smallest out of all those. Number 7. Let's see. I'm going to leave these up here in case I need them again. Let's see what the question is first. Which of the following arrangements is in order of decreasing size? Okay. So, let's see. Decreasing size. Do we have rubidium in there? No, we can get rid of that one. That just muddy water. How about argon? No argon either. All right. You know, we can approach this in a different way. Except that we've studied the atomic radius decreases from left to right and from bottom to top. So this is a decreasing radius for neutral atoms. But when you start making ions out of them, then you have to consider where are those electrons coming from and where are they going. If you're making a negative, where is it going? If you're making a positive, where did it come from? In order to judge the size change in the ion. Okay, so that's what's difficult about this one. All right, so we've got, let's just put them up there. Let's do a tally first. All right. The first one I see is gallium 3+. Okay. Then I see calcium 2+. Okay. Then I see potassium 1+. And let me go ahead and put the protons in here. 31. Calcium is 20. Potassium is 19. Okay. And then I see chlorine, 17. And then I see sulfur, which is 16. And then move down to B. Sulfur, chlorine, potassium, calcium, gallium is still there. I was looking for any odd ones, if they're all the same so far. Yeah, it looks like we've got them all here. And we need to arrange them in decreasing size. Okay. So we know that sulfur, chlorine, potassium, and calcium are isoelectronic. Because all you have to do is subtract 2 from this. 2 electrons from 20 is 18. That's argon. 1 from 19 is 18. 1 plus 17 is 18. And 2 plus 16 is 18. These are all isoelectronic with argon. Okay. Gallium, on the other hand, is bigger. This is a lot bigger, and it has, but look how many more protons it has. It's got 11 more than even calcium, right? So I'm wondering if gallium doesn't have enough nuclear charge that it could shrink that down even further than any of these. If we put these in order, if we put these in order, that's fairly easy because we've got the same electronic structure, and all we have to do is say, smallest one here is going to be calcium. And the largest one is going to be sulfur. So we would put sulfur 2- is going to be bigger than chlorine 1-, which is bigger than potassium 1+, which is bigger than calcium 2+. And then I'm tempted to put, even though gallium has these extra, right? It's got 4s, 3ds. But actually, it doesn't have any 4s's. It only has 3ds. So it's only got the third level, right? 3ds are in here. It still has those. But it's got so many more protons That's why I think gallium is smaller than all of them. Okay. That's not a very good explanation, but it's the best I can do. This makes a whole lot of sense right here. That one is kind of a guess for me. We'd have to look up the actual radius in order to verify it. But for now, that's a reasonable answer. Right. Number 8. In the reaction between magnesium and sulfur, the magnesium atoms do what? Between magnesium and sulfur, right? So this is a metal, so it's going to give up electrons. Sulfur is a chalcogen, so its preferred charge is 2 minus. Magnesium's preferred charge is 2 plus, because it's an alkaline earth in the second column. So what happened? Well, the magnesium atoms did what? Magnesium became cations. Right? We didn't get a polyatomic ion. We didn't share electrons because that's a metal and a nonmetal. So we transferred and made magnesium into a cation. That's typical for metals and nonmetal reactions. The metals become cations, the nonmetals become anions. Number 9. Choose the molecule with the strongest bond. All right. So we got A, B, C, D, and E is just dumb. So we won't even consider that one. All are equal. They're not all equal. We've got fluorine with a single bond, right? Fluorine has a single bond. Bromine, I think that's the right order. Yeah, bromine has a single bond. And iodine. These are all diatomic elements, and they have single bonds between them. All right. The strength of the bond is exhibited by, well, the amount of energy it takes to break them apart. So remember when we talked about what is it that that strengthens a bond? Well, that was ionic bonding, where we had coulombic forces, the size of the charge, the distance between them. That doesn't work for these because they're covalent. So we have to look at it from a different angle. And for this, we look at overlapping orbitals. Right? How much overlap can you get between this one, that one, that one, that one? Well, the closer you get the nuclei together, the more overlap you can get. So the strength of the bond should increase this direction. Because the size of the atoms are getting smaller. You get them closer together, they're overlapping actually lower energy bonds, lower energy orbitals. So we're decreasing the strength here. We would expect to go up here as the strongest bond, but it's not. It's not the strongest bond because by this time, you're looking at fluorine with only 1s and 2 orbitals. It's first and second here. And when you get those nuclei close together, those positive charges close together, they start to repel each other. And that weakens the bond. So the closeness of the nuclei negate any advantage you have from overlapping orbitals. So that's why this one is the strongest bond. I think that's why I threw that one in there, because it was a curveball. All right. How about number 12? Oh, hold on a second. Here we go. Draw Lewis structures of the molecules below and then use them to answer the following questions. So we're going to answer, looks like just 12. 12 using these molecules. First one is boron trihydride, nitrogen dioxide, see it better this way, sulfur hexafluoride, ozone, and phosphorus pentachloride. All right. So we have to draw the Lewis dot structure. And then the question is, these molecules have 0 net dipole. So remember what we need to know in order to determine whether a molecule has a dipole. We need to know the polarity of the bonds. Does it have polar bonds? And the geometry. Is there a net, a vector addition of the dipoles of those bonds that gives an overall dipole for the molecule? Okay. So boron trihydride, let's tally up the valence electrons first. Boron is 3 plus 3 is 6. Okay. Nitrogen is 5 plus 12 is 17. These are valence electrons. We have to do that before we can draw the Lewis structure. 6 times 7 for fluorine is 42, plus 6 is 48. Okay. Ozone is 3 sixes, 18. And phosphorus is like nitrogen, it's 5, plus 35 is 40. Okay. Now we can start building. And this is kind of like Henry Ford. I got an assembly line here. First thing I wrote that, then the next I calculate these, and then I do the Lewis dot structure. The boron's in the middle. We have 3 hydrogens, 2, 4, 6, used them all up. That's your structure. Well, that's the beginning. We'll do the next step in a second. This one has nitrogen in the middle. Then we put 1 bond for each of the oxygens. That's minus 4 would be 13. So 2, 4, 6, 8, 10, 12, 13. Okay. Now we need double bond. We need an octet for nitrogen. We're not going to do it. This is one of those oddballs. We can make a double bond on one side or the other, right? But we're going to have an octet deficient nitrogen in this case. It's either that or make another double bond here, and then you'd have an excess. We usually go for the deficient if it's choice. Okay. So let's see. Did I get all 17? 2, 4, 6, 8, 10, 12, 14, 16, 17. This one is a little better behaved. Fluorine, 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 fluorine. That's 2, 4, 6, 8, 10, 12. So that's 36. So if I put 6 around each one of these 6s, that'd be 36. That'd be all the electrons used up. And we have exceeded the octet. Okay. Then ozone, right? Which one goes in the middle? Doesn't matter. They're all three the same. So this is 2, 4 minus 4 is 14. So we start on the outside and work our way in. 2, 4, 6, 8, 10, 12. And then the last 2 go here. And in order to make an octet on that central oxygen, we're going to make a double bond. So that's 2, 4, 6, 8. All right. And the last one, PCl5. So we have phosphorus, 1, 2, 3, 4, 5 fluorines. There we go. 2, 4, 6, 2, 4, 6, 8, 10. So now we're down to 30. And if we put 6 around each one of these, times 5 would be 30. Oops. That creating electrons. Okay, so this is the rough estimate of the Lewis dot structure. Now we want the molecular structure. So what you have to do is the electronic structure first. This would be trigonal planar. So we have boron like this, there, that. So do we have polar bonds? Slightly polar. Even if we did, they're regularly spaced around an isosceles triangle. They cancel each other out. This is nonpolar. How about this one? Well, how many groups do we have? 1, 2, 3. So we have to draw it like this. That, this, like that. That's a bent molecule. With the difference between nitrogen and oxygen, those bonds are very, maybe slightly polar, but, and toward the oxygen, just very slightly toward the oxygen. But we've also got this lone, this is a free radical. Right? Unpaired electron in a molecular structure means free radical, right? They're extremely reactive. So I would say this is probably very unstable to begin with. But this is possibly polar. This one is 6 groups around the central atom, which means what? Octahedral. This is bent. That's why I think it's polar also. So octahedral means nonpolar. Those bonds are definitely polar, right? They go in this direction. But if they're regularly spaced in an octahedron, they cancel each other out. We can say the same thing for this one, only this one's not octahedral. It's a trigonal bipyramid, but it's nonpolar because all the polar bonds are pointing to balanced positions that cancel each other out. This one would be here, here, like that, that. This is definitely polar. It's a bent molecule. You both might call it angular. I like bent. Okay, so what was the question? 0 net dipole. Which one has no dipole? This one and this one. So this is Roman numeral 1 and 3 and 5. 1, 3, and 5. That would be B. That one ate up the clock, as they say in the sports world. There, the same case. Unless I need the space, I leave it there. Sport. Use a waxing. 13. All right. how many electrons must be shown as bonding or non-bonding in the Lewis structure whose skeleton is as bonding or non-bonding? That means all the electrons are counted up, right? So we got 1, 2, 3, 4 carbons. That's 4 times 4. Okay. And we have, let's see, 1 oxygen, which is 6. And hydrogens, 1, 2, 3, 4, 5, 6 hydrogens. Right. So that's 28. Yeah, 28 electrons. Okay. Now this is an organic structure. And one of the first things you learn if you take organic is that carbon can have 4 bonds. It just simplifies the whole process. Just know that carbon has 4 bonds. So C1 is good already. C2 only has 3, and C3 only has 3. So there's probably a double bond between 2 and 3. And then C4 only has 3 bonds. So it needs another double bond, but it can't put the double on the other side with that carbon. It has to put it on the side with oxygen. So that's where you end up. We skipped that one. Because you're probably not interested in organic anyway. All right, number 16. In the Lewis structure, ICl2 minus. Okay. How many lone pairs of electrons are around the central iodine atom? All right, so we got to draw the structure. We got 1, 2, 3 halogens, which means 21, plus 1 for the charge. So we have 22 electrons. Iodine's in the middle. So that's minus 4, which is 18. 2, 4, 6, 8, 10, 12. They're done. So that's what? 6 electrons left over. They have to go here. 2, 4, 6. Now let's go back to the question. How many lone pairs? How many lone pairs? Not how many electrons, but how many lone pairs? 3 lone pairs. Okay. That wording can mess you up. If you got your mind set on one thing and the problem says something else, then you shoot yourself in the foot. How about 19? How many resonance structures can be drawn for the molecule O3? We did O3 just a minute ago. I guess I'm going to have to do it again. All right, so we have 3 times 6 is 18. So we have an oxygen. There, so that's 4, 14. 2, 4, 6, 8, 10, 12, 14. Now, when we talk about resonance structures, Lewis dot structure says, the procedure says that we can make a double bond on this side or on this side out of these electrons. It wouldn't do us any good to make it out of those two because that wouldn't help us any. It's already 1, 2, and 3. 6 electrons. We need 2 more. So if we put it there, that would be 1. Or if we put it on this side, that would be the other one. So you have 2 resonance structures possible for ozone. All right, 20. Which of the following types of molecules always has a dipole moment? All right. A, B, C, D, and E always has a dipole moment. Linear molecules with two identical bonds. So linear molecule with two identical bonds, that's nonpolar. Definitely. That's always nonpolar. But the question is, which one is always polar? Right, so the first one is nonpolar. Right? That doesn't fit. How about B? Tetrahedral molecules, four identical bonds, equally spaced. That's another nonpolar. How about C? Trigonal pyramid molecules, three identical bonds. How do you get a trigonal pyramid? You don't get a trigonal pyramid from our regular structures, right? It goes linear, trigonal planar, tetrahedral, trigonal bipyramid, and octahedral. There's no trigonal pyramid in there. The only way you get a trigonal pyramid is if you start with a tetrahedron, right? And you have something out here, 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 and you can only have a trigonal pyramid if that position is a lone pair. So trigonal pyramid should always have a dipole moment, simply because it has that lone pair. Right? This is always polar. We found our answer. The other two, well, none has a dipole moment. E can't be right because we found one that negates that. Trigonal planar molecules with three identical bonds, that's always nonpolar. All right, so we found our answer. And what's a good example of this one? Ammonia. That's my fallback position. Ammonia. Okay, 21. Which set contains atoms listed in order of increasing electronegativity? All right. So increasing electronegativity, let's remove these. And we know electronegativity is going to increase from lower left to upper right. So we've got fluorine is going to be here. All right. Then nitrogen is going to be 1 over. Let's put oxygen there, nitrogen there. Let's just fill these in. Carbon and boron. We may not need them, but I'm going to put them in there. Silicon. Silicon is below carbon. So it's going to be here, like that. And then phosphorus is a pnictogen. It's right here. Nitrogen, we got it already. Oxygen, fluorine, oxygen, chlorine is right here. What's under oxygen is sulfur. Chlorine, fluorine, sulfur, oxygen, fluorine. Okay, so they're all there. All right, we want to put them in increasing electronegativity. Lower left, upper right. We're not going to need boron, so we'll leave that one out. Carbon's in there. So the least electronegative should be silicon. And then, let's see, it's a toss-up. You go up to the right, and it could be carbon. It could be carbon or phosphorus. And then we have nitrogen. Let's see, sulfur would probably be down here. And chlorine. And then we would go up to nitrogen, oxygen, and fluorine. So let's see, which one includes these? Fluorine, A, fluorine's on the wrong end. B, fluorine's on the right end. Then oxygen, then nitrogen, then phosphorus. So that's a good one. B is a good one. And since we don't have any wonky ones like none of the above, two of the above, then we found our answer. And you can go in there and look at the rest of them and see, but I think B is going to get you there. Uh, 22. Which choice has the bonds listed in the order of increasing bond energy? All right. And we have a D all the same. I kind of doubt that one. So we have increasing bond energy, HF, HCl, HBr. Then we have single carbon, double carbon. That looks like a good candidate, actually. It's definitely increasing. That's a good candidate. We talked about this one earlier. This is the strongest one of that bunch. So we know that's not it. D, the nitrogen. Oh, this one. When they say dinitrogen, that's what they're talking about right there. And they're saying this is less than the carbon-carbon in C2H4. C2H4 would be a double bonded carbon. And then C2H6 would be a single bonded carbon. Right. So we don't even have to look at this one. This is in the wrong order anyway. So actually we found our answer right there. Single, double, triple, increasing bond energy. What do we mean by bond energy in a quantitative sense? Bond energy is listed as the amount of energy it takes to break the bond. The bond's already there. You put energy in to break it. So those values are always positive numbers because the system is the bond and we're adding energy to it. So they're going to be positive. And in the other case, when you get the gaseous atoms coming together to form the solid, you get the release of energy, the exact same amount. 23. Lattice energy, that's what I was trying to think of. In the gaseous phase, which of the following diatomic molecules would be the most polar? There are two things to consider here. One is difference in electronegativity. That's our first clue. So let's put cesium fluoride, which is the farthest apart. Cesium chloride, which is a little closer. Sodium chloride, which is even closer. And sodium fluoride, which is not quite as close as those. And then lithium fluoride. So which ones have the furthest apart? Cesium's way down here. Fluorine's way up there. It's the furthest apart. So actually, I don't have to invoke any trying to think of the right word, oddballs, non-standard explanations. In this case, you can go to, since they're all ionic, then you can go to the difference in electronegativities to show the most polar. And actually, they would be all polar. Actually, they're all polar that direction. Actually, they're all ionic. So actually, I would say that question is not good unless you take them at their word and say, even ionic bonds can be polar. Right? When we introduce the topic, we use polarity in terms in describing a covalent bond, not an ionic bond. But the difference in polarity between the two electronegativities tells us that the electrons are going to spend most of their time, actually all of their time, around fluorine. That's a bad question. I don't know why I put that one in there. Maybe just to show you that it was a bad question. But if that one pops up on an exam, you'll know how to approach it, even if it is a bad one. 25. Which of the following ionic compounds has the largest lattice energy? The lattice energy most favorable to a stable lattice. Okay. Let's see. I think this one is 1, D, E. So we have barium sulfide, sodium bromide, cesium iodide, beryllium oxide, and barium oxide. Okay. We look at this from two different, need to incorporate two ideas here. One is the charge on each of the ions and the distance between them. So we're talking about Coulombic forces because these are all ions. So we're looking for largest lattice energy. That is the largest amount of energy you get back when the gases of this cation combine with the gaseous form of that anion to make a solid. That's what the lattice energy is, the greatest amount of energy you get out. So which ones have 2+ charges? This one is a 2+, 2-, 2+, 2-. Yep. This one is a 1+ and 1-, 1+, 1-, and a 2+, 2-. So if we start eliminating based upon the charge difference, we would throw this one out and that one out. These are all 2+ and 2-. Then we say which ones are closest together. We want something that's small. Barium is huge. All right. So I throw that one out. Beryllium and wait, did I throw that one out? Yeah, barium oxide. Well, barium, throw that one out too. The smallest ones here with the 2+ charge, beryllium and oxygen. Beryllium is a tiny ion, gets very close to the oxygen. So that's why we say that beryllium oxide should have the largest lattice energy. Right. 27. Using the following reaction data, calculate the energy of an HF bond. Okay. Dickens. Wait. Oh, I think the list is dropped also. Pretty sure. All right. So if we want to know the energy of an HF bond, we could use that information. How would we define the energy of an HF bond? That's the formation, the energy of formation, right? The enthalpy of formation. So we're looking for delta H formation. How do you do that for HF? Remember, you start with a product. HF is a gas. And it forms from the most stable forms of each of the elements. Fluorine, gas, diatomic. Hydrogen, let's see, let me do that. Hydrogen, diatomic gas. Okay. We only need one of each. So we're going to say a half here and a half there. That's the target equation that we're working for. And we're going to use, my mind's gone blank. Hess's law, sorry. Hess's law to answer the question. Okay, so if we have H2 and F2, let's see. Hold on a second. Energy of an HF bond. Notice that first equation is just twice this equation. But that doesn't appear to be the answer. You see, I must be barking up the wrong tree. Oh. Okay. I am barking up the wrong tree. If we're going to determine the energy of the bond, we need HF in gaseous state because we don't want any phase change to interfere with it. And it's going to produce separate atoms. That makes more sense. Right? Because we just broke that single bond to make these individual atoms. Yeah, that's our target equation. So now we can say, all right, HF, which one of those has HF in it? The first one, right? But it's on the wrong side. And gas yields. I'm flipping that first equation. H2, F2. And the delta H for this one, after we flip it and we divide by half, divide by 2. Then we get rid of that, takes this one to a half and that one to a half. And the delta H, we have to change the sign and take half of it. So it'd be a positive 542 divided by 2. I'm not going to trust mine. My mind's not sharp enough today. 542 divided by 2. That's 271. So this is, instead of negative 542, it's positive 271 kilojoules per mole, or kilojoules for that reaction. Okay, so that takes care of this one. All right, let's, how do we do? Which one's got hydrogen in it? The next one has hydrogen in it. Excuse me. H2 gas yields 2 hydrogen gas. But we only need 1. So we got to take a half of this one. And that value is 432. We didn't flip it, so we keep positive 432, but we have to take half of 432 also, which is 216. Okay, takes care of this one. And that's a half here and 1 there. Okay, and we do the same thing for fluorine. I think there's an equation, the next one coming up. Fluorine gas, and then 2 fluorines. Yeah, that's the last one. And it's 154. We got to take half of this one. So half of that and then that. And so we cut that one in half. 154 should be 77. Now we can add them together. Plus 564 kilojoules. Yeah, I'm going to run out of time. So I'll have to come back to finish the video. All right, 28. As indicated by Lewis structures, which of the following would probably not exist as a stable molecule? A, B, C, D, E. All right, first one is methanol. The next one is formaldehyde. This one, I don't know what that one is. C2H2, C3H4. I know this one, I know that one, I know that one. So it's probably one of these two right here. If we draw the Lewis dot structure for this one, it would look something like this. Like that. Formaldehyde is going to have hydrogen here, 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 oxygen there, and 2, 4, 6, 8, like that. This is acetylene. It's going to look like this. And you can draw the Lewis dot structures, follow the rules. That's what you'll get. Now this one, we're going to do this one longhand. So that's 4 plus 3 plus 6. That's 13 electrons. All right, we put carbon in the middle, and we put 1, 2, 3 hydrogens, and an oxygen. That's 2, 4, 6, 8. Minus 8, it's 5 electrons. 2, 4, 5. It's not likely. Plus, we can do the formal charge on this. What we formal charge here? Well, 4 is the valence electrons for carbon, and 1, 2, 3, 4. So the formal charge on carbon is 0. Right? It's okay. Oxygen is 6 minus what? 1, 2, 3, 4, 5, 6. Right, well, that's 0. Trouble is, that is a free radical, and they're not too common. But we'll leave it alone for now. How about this one? 3 times 4 is 12, and plus 4. So we have 16 electrons. We have 1, 2, 3 carbons, and then we put 1 hydrogen here, 1 hydrogen there, 1 hydrogen here, 1 hydrogen there. So that's 3 carbons, 4 hydrogens, 2, 4, 6, 8, 10, 12. 4 electrons. We can't put any more electrons on hydrogens, so we have to move in. All right, 4, so we could put 2 here and 2 here. So that would give you an octet for this carbon and that carbon, but not for this one. So the best way to do that is to go here and here. 2, 4, 6, 8, 10, 12, 14, 16. We didn't create any electrons. And that is reasonably stable. 1, 2, 3, 4, 1, 2, 3, 4. So all these carbons have 0. And there are no free radicals. So this is probably the least likely, this one right here. Okay. Not that it doesn't exist, it's just this is the least likely. Not stable. Free radicals are the guys that go into your body and tear things up. Actually, most of them are created in your body from biochemical reactions. And that's why you want to have a diet rich in unsaturated fatty acids, vitamin C, other vitamins that scavenge free radicals. That usually means bonds that are unsaturated. What do we mean by that? That comes from organic chemistry. A saturated bond between 2 carbons is the carbon has Single bonds all around. If it has any double bonds, then it's unsaturated. That's as far as I can go in 30 seconds. Okay, 29. Did we got to when? 1:45. 12 minutes. I know I'm not going to finish. Electronegativities. Carbon is 2.5, hydrogen is 2.1, chlorine is 3, and oxygen is 3.5. From the following group, the molecule that fits the given state. So those molecules, A, B, C, D, and E with parentheses. This molecule contains a carbon atom with trigonal planar geometry. So notice you don't need to know the electronegativities to answer this question. That's just blue smoke that the questioner created, blowing in your face to try to confuse you. All you need to know is the Lewis dot structure and derive the VSEPR geometry. Okay. Let's see. Molecule carbon with trigonal planar geometry. Right? So we've got CH3CHO. And when we write organic compounds, these hydrogens all belong to that carbon. And the next bond for that carbon is with this carbon. That's how we write it. Okay, next, CO2, CH3, Cl, C2H6, and 9. So we're looking for trigonal planar for the carbon. All right. This one is going to have these two carbons bound together. It's going to have those hydrogens there. So that's tetrahedral. This one will have a hydrogen here, and it'll have an oxygen there. You can draw the Lewis dot structures and prove that to yourself. That means this one is trigonal planar. There's 3 groups attached to it. We know that carbon dioxide is linear. We've drawn that so many times. I have it memorized. This one is going to come out like this, this, with that chlorine, right? That's tetrahedral. This one is C2H6. Draw it out. Room for all these hydrogens. 4 groups around each carbon. Those are all tetrahedral. And that's nothing. So the one that has trigonal planar is A. Right. In the interest of time, I'm sort of taking shortcuts. You can prove it to yourself. Just draw out the Lewis dot structures and you'll see that's true. Let's see, 34. Right? I didn't skip any, did I? Okay. Of the following, which molecule has the largest bond angle? All right. See. So we've got ozone. We've got OF2. Got HCN. And H2O. And more than one of the above, equally large bond angles. All right. We know that hydrogen cyanide, if you draw the structure out, it's going to look like this. That is 180 degrees. That's a linear molecule. Okay. We know this one is bent. So it's nominally going to be 120 degrees bond angle. Water, it starts as a tetrahedral and it has 2 lone pairs, so it's going to be squished. It's going to be, the tetrahedral angle is 109.5, but it's going to be less than that because those lone pairs are squishing that bond down. So far, this one's the largest bond. And then OF2, if we drew that one, there'd be 6, and 2 times 7 is 14. That's 20 electrons. Oxygen in the middle. Fluorine, that's 4. That's 16 electrons. 2, 4, 6, 8, 10, 12, 14, 16. So that central atom is going to be tetrahedral. And it's going to be bent. It's going to be kind of like water. So it'll be less than 109.5. So this is our largest bond angle, that linear molecule. We had the time, I'd break and pick it up on Thursday, but we don't. Can't get everything in. 35, right? Got time for one more. Which of these are non-polar overall? So the first one is sulfur tetrafluoride, sulfur difluoride, carbon tetrachloride, hydrogen sulfide, and OCl2. And we're looking for non-polar overall. All right. If you're in a hurry on a test and you've got that question, and carbon tetrachloride is one of them, that's your answer. It's tetrahedral, right? The rest of them, this is bent. It's like a water molecule. This one's more than likely bent. This one's going to have some lone pairs. This one's going to have some lone pairs. So that changes the geometry such that you have a vector sum with a dipole. Right? You could draw those out. Yeah, maybe I should. And then pick it up with 36. You want me to do that? Okay. This one is 6. And this is 4 times 7 is 28. So it's 34. Sulfur. Fluorine. Which is 2, 4, 6, 8. 8 from that is 26. Yeah, 26. 2, 4, 6, 8, 10, 12, 16, 18, 20, 22, 24. So we have 2 electrons left over. They go right here. All right, so this is 1, 2, 3, 4, 5 is trigonal bipyramid. Well, a trigonal bipyramid is going to have something up here and something down here. With a trigonal bipyramid, if you have a lone pair, where's the lone pair going? It goes on the triangle. And the rest of them are the fluorines with the sulfur in the middle. So what's our structure there? That's a seesaw. Take it, turn it on its side. You have these 2 legs on the bottom, and there's your seesaw board. So that one's polar. SF2 is 6 plus 14, which is 20. And then we have F, which is minus 4, 16, 2, 4, 6, 8, 10, 12, and 4 more. There. That's tetrahedral, and this molecule is bent. So it does have a dipole. And H2S is like water. It's bent. Because sulfur's a chalcogen. It behaves similarly. Okay. Well, which of the following molecules are nonlinear? I guess we better pick it up with 36. I'll pick it up with 36 and then post the video. Let me put this as a reminder. That's where I start after the lab. And number 36. Which of the following molecules are nonlinear? Okay, so let's put those molecules up here and determine what their geometry is. C2H2 N3. That's the azide ion. Hydrogen cyanide. CO2 and H2O2. CO2, H2O2. Okay, nonlinear. So let's start with Lewis dot structure. Okay. This is 5 electrons, and 2 times 6 is 12 plus 1. Right? So that's 18 electrons. This is 2 times 4. Yep, it's 8. And 2 times 1 is 2, so that's 10 electrons. This is 3 times 5, which is 15 electrons. Oh, 15 plus 1. 16 electrons. And this is 1, 4, and 5, which is 10 electrons. This is 4 plus 2 times 6 is 12. That's 16 electrons. And this is 12 plus 2 is 14. Now we can draw our structure. NO. So that's 2, 4. 14 left over. 2, 4, 6, 8, 10, 12, 14. Okay. So what electronic structure is this? This is trigonal planar. When you cover up that one, the molecule now is bent. So that's all we need to determine. It's nonlinear, right? So this one's nonlinear. That's good. How about this one? C2H2. All right. Carbon, carbon, hydrogen, hydrogen, 2, 4, 6. That's 4. So we have 2, 4. And we got to make an octet here. So we take 2 of those, make a double bond, take 2 of those, make a triple bond. This is linear. Okay. Yep. This is linear. Azide. This is 3 nitrogens connected, right? 2, 4. So that's 12 electrons. 2, 4, 6, 8, 10, 12. And we need, by the way, when I write this one out, it should have a negative sign there. So we need to make an octet. So what if we put a double bond there and a double bond here? So that's 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. That should be linear. Okay. And it also should have a negative sign. Hydrogen cyanide, we've done that one before. That's linear. Carbon dioxide, we've done that one before. That's linear. H2O2. Okay, so we have an O and an O and an H and an H. 2, 4, 6. So that leaves 8. 2, 4, 6, 8. So oxygen, each oxygen has an octet. But around this oxygen is electronic tetrahedron for both of them. But when we cover up the lone pairs, we get a bent molecule. So this one's bent, bent. Right? It's bent here and it's bent there. That's nonlinear. So this one is nonlinear and that one's nonlinear. Right? So hydrogen peroxide and the nitrite ion are nonlinear. These two right here. Okay. That's 36. Okay. 38 coming up. Okay, 38. The molecular structure of BRF6 plus. So we've got 7 halogens times 7 valence electrons is 49 minus 1. So we have 48 electrons. Bromine is going to be in the middle. And we have 1, 2, 3, 4, 5, 6 fluorines. Okay, 2, 4, 6, 8, 10, 12. Minus 12 electrons equals 36 electrons. So 2, 4, 6 times 6 is 36. That uses all of the electrons. And the question was, what's the molecular structure? Well, we've got 6 groups around our central atom. 6 groups means octahedral. That's the molecular, that is both the electronic structure and the molecular structure, because we have no lone pairs around that central atom. So that's good for the molecular structure as well, octahedral. $39. What type of structure does xenon OF2? Okay. Noble gas has 8. Oxygen is 6. 2 times 7 is 14. So that's 28. 28 electrons. Okay. Xenon's going to be in the middle. And we have an oxygen, we have a fluorine, and we have a fluorine. So that's 2, 4, 6, 22 electrons. Okay. 2, 4, 6, 8, 10, 12, 14, 16, 18. Right, so that's 4 electrons. 2, 4. Okay. The electronic structure is 1, 2, 3, 4, 5. That's a trigonal bipyramid. Right? So we're going to have xenon in the middle. And where do these go? If we have lone pairs in a trigonal bipyramid, the lone pairs go on the triangle. Okay? So that means one of these, say that's oxygen, this is fluorine, and this is fluorine. I'm just speculating, but it's going to be a T shape. T-shaped molecule because there's a bond here, there's a bond there and a bond there. When you turn it on when you rotate it around, this oxygen sticks out here like that. That's a T-shape. .44. Select the correct molecular structure for silane. All right. Silane is, well, the naming convention is derived from CH4. Right? CH4 is methane. Meth referring to the carbon. And this one would be, silicon would be silane instead of methane. Okay. Now, since silicon and carbon are in the same group, we should expect them to have similar molecular structures, and they do. If we draw out the structure here, we're going to get a tetrahedron. And it's going to look like silicon here. It's going to have in the back is a hydrogen. Then we're going to have a hydrogen here. We're going to have a hydrogen here, and then a hydrogen there. So we get this triangular base, and then the regular structure is a tetrahedron. Right. 46. Select the correct molecular structure for beryllium dichloride. Actually, we don't have to say dichloride. Beryllium chloride, because beryllium has a 2+ charge. It's an alkaline earth. Chlorine always has -1, so we have 2 of them. So the proper name for this would be a type 1 compound, beryllium chloride. Now, to draw the structure, beryllium has 2, and 2 times 7 is 14, so we have 16 electrons. All right, so we put beryllium in the middle. Put chlorine there, that's 2, 4. -4 is 12. I think I did that right. 2 times 7 is 14. 16 is 4, 12, okay. 2, 4, 6, 8, 10, 12. Okay. Now we can make an octet for beryllium like that and like this, and that would work. The problem is, well, beryllium does have p orbitals. They can overlap. So this would be my first choice. The problem is, what's the formal charge? The formal charge on beryllium, well, actually, beryllium has a charge already. It's 2+. And if we say 2 electrons and then 2 from here, this would be preferred. That would give a formal charge of 0. These would have a formal charge of 0. And actually, if we do that calculation, this is preferred with a deficiency of the octet. And you could probably make an argument for doing it the other way also. But the question was, what's the molecular structure? And that's linear. Either way, this molecule is linear. All right, 48. 48. In the molecule xenon difluoride, how many pairs of electrons surround xenon? What's the molecular geometry? Okay. So we have 8 electrons here. We have 2 times 7 is 14. So we have 22 electrons. Xenon in the middle, then the fluorines. Okay. Minus 4 is 18. So we have 2, 4, 6, 8, 10, 12, 14, 16, 18. How many pairs around the xenon? 3 pairs. Okay. Now, what's the structure? 1, 2, 3, 4, 5. So we have 5. Yeah, we have 5. That means it's electronically, it's a trigonal bipyramid. But if we put the xenon in the center, and we're going to have something here and something here, where do the lone pairs go? In a trigonal bipyramid, the lone pairs go on the triangle. And the fluorines go here. So when you cover up the lone pairs, you get a linear molecule. This molecule is nonpolar. So C, 3 lone pairs, linear structure. Okay, 49. 49. Choose the member of each set that best matches the label. All right. So we have beryllium and barium. Beryllium and barium, and we want the more metallic. Okay. The second one, more covalent. And that would be N2O, yes, versus MgO. So, and the last one, highest electronegativity. Highest electronegativity. And we're looking at oxygen, sulfur, bromine. Okay. So which one is more metallic? Well, the more metallic is the one that has the smallest electronegativity. Farthest to the left, closest to the bottom. So barium is in the same family as beryllium, but it's much lower. Now, what do we mean by metallic? Metallic refers to the tendency of an atom to give up its electrons. Right? So it takes very little energy to get a ground state electron off of barium. It takes a little more energy to get it off of beryllium. Right? So this one would be the more metallic. How about the more covalent? Look for metal, nonmetal, or metal, or nonmetal, nonmetal. This is a metal, nonmetal. That's ionic. This is a nonmetal, nonmetal. So it's more covalent. And the highest electronegativity would be the furthest to the top and to the right. So oxygen, sulfur is below oxygen, and then bromine is way down here. So I would say oxygen would be the more electronegative. So we have barium, nitrous oxide, and oxygen. Barium, nitrous oxide, and oxygen is E. So our answer is E. Right. 50. Use the bond energies given below to calculate the enthalpy change for the reaction. All right. So we have our reaction here, HCN, hydrogen cyanide gas, plus two hydrogen gas yields H3 NH2 gas. So this is methylamine. Okay, we want to calculate the enthalpy for this reaction, delta H. What we need to know is the nature of the bonds. This hydrogen cyanide, we've done that one before. We've got an HC bond and a C triple N bond. This one is a simple HH. This one has CH's right here. It has a CN and it has an N as NH's. Now, let's draw the Lewis structure on this one to be absolutely certain. So we have 4, 3, 5, and 2. So that's 14. 14 electrons. So we have carbon, nitrogen. We have hydrogen and a hydrogen. And we have 3 hydrogens here. Okay. 2, 4, 6, 8, 10, 12. So that's 2 electrons left over. Where do they go? Carbon's full. So we put these 2 electrons here, like that. And that gives the duets for hydrogen, the octets for carbons and nitrogen. We only have single bonds. So we've got 2 hydrogen bonds here. We have 1 carbon nitrogen, and we have 3 carbon hydrogens. Here we have 2 hydrogen hydrogens. We have a carbon hydrogen, one of those, and we have 1 carbon triple nitrogen. Right? So remember the calculation of delta H is the summation of the energies for delta H's for broken bonds minus the sum of delta H's for created bonds. Okay. The reason we do it this way, rather than the bonds formed minus the bonds broken, is that the values here are all positive. This is the amount of energy you put in to break the bonds. This is the amount of energy you get back. Since these are all positives, then the energy you get back must have a negative. So our calculation is this first group, the bond's broken. We broke 1 carbon hydrogen, 1 carbon triple bond nitrogen. So carbon hydrogen is 413 plus carbon triple nitrogen, 891. There's only 1 each, so we multiply each one by 1. And then 2 hydrogen hydrogens. So we need 2 times, what's the HH bond? 432. There. Now we subtract the bonds formed, created. All right. Let's see. On this side, we have 3 carbon hydrogens. and we have 1 carbon nitrogen, and we have 2 nitrogen hydrogens. So if we combine what we've done, oh, no, I'm sorry. I'm doubling up. This is an explanation of that. So we only have 3 carbon hydrogens, 3 carbon hydrogen, 413. And then 1 carbon nitrogen, 305. And then 2 nitrogen hydrogen, 391. There we go. That's the hard part. That's the thinking part. The rest is number crunching. So, how do I get rid of it? Clear? Oh, well. Okay, so we're going to add these up. 413, 891, and 432 times 2. Okay. This value here is 2168 kilojoules. Right? Yep. And this one over here is 413 times 3 plus 305 and 2 times 391. This one is 2326 kilojoules. And there's a negative between them. So we subtract that one from this one, and we get an overall of minus 158 kilojoules. Okay? That was 50. All right, next, 51. All right. We're given the following information. Sublimation, bond energy, ionization energy, electron affinity, lattice energy, and another bond energy. Those are individual equations that we can use to calculate the change in enthalpy when lithium solid is reacted with hydrogen bromide gas to yield hydrogen gas and lithium bromide solid. This is a Hess's law problem. So I put the target equation at the top. 2 lithium solid plus 2 HBr gas yields hydrogen gas plus 2 lithium bromide solid. Okay. So we're taking one at a time. Which one has lithium in it? Well, lithium solid, the first one has lithium solid. And that's the only one. So we're going to take the lithium solid first. Remember Hess's law, we can add up the energies once we've made the proper adjustments. Lithium solid here yields lithium gas. So lithium solid yields lithium gas. And that enthalpy is 166. So delta H, 166 kilojoules. The problem is we need two of them. So if we multiply the whole equation by 2, now we get 332, right? 16 is 12, carry the 1, here's the 1, carry the 1. Yep, 332. Okay, so we've taken care of this one right here. The second one is HBr, hydrogen, and bromine. That's the bond energy of HBr. Here is HBr, and it's on the correct side. So we need HBr gas is yielding hydrogen and bromine atoms. Hydrogen plus bromine. Right? But we need two of them. So if we put 2, 2, 2, then we go back to 363 kilojoules and multiply by 2. Right? 2 times 6, 12, 726. Okay? That takes care of this one. Then if we go to the next one, lithium gas split apart into ions. So lithium gas split apart into ions. Where's the lithium gas? Well, here's the lithium gas right there. But I'm inclined to skip that one and go to hydrogen. Let's find the one that has hydrogen gas in it. That's the last one. And it's on the wrong side in that equation. So we have to flip it. It's the right number of moles, but it's on the wrong side. So if we flip the equation and put hydrogen gas on this side, and then when we flip the equation, that put 2 hydrogens on this side, that, right? Yeah. 2 H's on this side, H2 on that side. Then 432 kilojoules for the bond energy has to change the sign. So we're minus 432. Right? That takes care of this one right here. Now how about lithium bromide? Lithium bromide we find in the next to the last equation, and it needs to be multiplied by 2. It's on the correct side. So lithium bromide solid, yes, and the lithium ions and bromide ions are on this side. By the way, this is lattice energy. We defined that earlier. But we need 2 of them. So the value for that is minus 809 times 2. So we have 18, carry the 1, and then 16. So minus 1618 is for this one after we multiply the whole thing by 2. And that takes care of this one. Okay. And this one. So how about these others? Well, this one cancels right there. Okay. And let's see. We have to work on these ions. Let's look for the ions. Right? The third equation down has lithium ion in it and needs to be on the side that will cancel. So lithium ions on this side, we need lithium ions on this side, and that's exactly the way it's presented. Lithium gas yields lithium ion gas plus an electron. Okay, that doesn't take care of this one. We need to multiply by 2, 2, 2, and 2. So what's the energy expenditure for this one? We have to put energy in to make it work. So we need to double the energy of 520. So that would be 1,040 kilojoules. Okay. What does that do for us? Well, this 2 lithium gas cancels that one. And this 2 lithium ion cancels that one. So now let's look for bromine. Br plus E electron. So Br, and is it on the right side? We want the ion to be on the right side. So it will cancel this one. So yes, the way it's written is correct, only there's not enough of it. So Br gas plus electron yields Br minus gas. But we need, and this, I should move this down over here. It's not a charge, it's an addition. So if we want to cancel these 2 bromines, we need to multiply by 2. That means the value that's given there for the enthalpy is minus 325. We need to multiply that by 2, minus 650. Now, that cancels the electrons and the 2 bromines and the 2 bromide ions. So cancel, 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 leave that one, cancel, cancel, leave that one, that one. So we've got this, that for here, we've got this for here, and the rest cancels. Now we can add the values. Let's see, 332 is positive, 726 plus, 432 minus, 1618 minus, 1040 plus, and 650 minus. So that means we've got an enthalpy for that reaction of a minus 602 kilojoules. Okay. It took a lot of work. You have to be very methodical about it. Next, 52. All right. I included 52 because it's similar to 51, only it's more cryptic. In other words, it's got the symbolics that go with the enthalpies. All right, if we're going to calculate the lattice energy for rubidium chloride from the following data, what we need to do is settle on our target equation. So the question says lattice energy for rubidium chloride. The lattice energy is the energy that's given up when this happens. Rubidium chloride. So rubidium is an alkaline metal. And chloride is a halogen. That's the solid. And this is formed from rubidium ion as a gas plus chloride ion as a gas. That's the enthalpy that we want. Okay. What we need to do is interpret what we see there. And I'm going to have to put that over here. I think maybe off to the side would be best. So rubidium solid to rubidium gas is sublimation. So we'd say rubidium solid to rubidium gas is sublimation, and the enthalpy is 85.8. Okay. The next one is IE1. That is ionization energy. First ionization energy for rubidium, which means what? Well, rubidium gas has to be a gas. We add energy to it, and we get rubidium plus an electron. Okay, and that value is 397.5 kilojoule. Okay, the third one is BE. What does BE stand for? Bond energy. Bond energy is going to be chlorine gas, which yields separate chlorine atoms. And the value for that is 226 kilojoule. Okay. The next one is heat of formation for rubidium chloride. The heat of formation, remember, rubidium chloride in its standard state, which is a solid, is formed from rubidium in its standard state, which is also a solid, plus chlorine in its standard state, which is a gas. So we need 1/2 of that. That's the heat of formation. The expression for the heat of formation, minus 431. Okay? And the last one, EA, electron affinity. Chlorine as a gas plus an electron yields the chloride ion as a gas. And the heat that's given up is 332 kilojoules. So that's the interpretation of each one of those enthalpies given in the question. Now, this is our target equation. So let's see. Let's work rubidium plus. Where's rubidium plus? Right here as a gas. That means it needs to be flipped. So if we write this equation in here, rubidium plus as a gas yields plus an electron, excuse me, rubidium gas like that. Then we have to invert, we have to change the sign. So this one's going to be minus 397.5 kilojoules. Okay. That one's done. Okay. And that takes care of this one, there, and there. Now, how about chloride? Chloride on the left-hand side. Well, here's chloride on the right-hand side, so we got to switch it to the left-hand side. Chloride gas then would yield chlorine gas plus an electron. And all we have to do is change the sign, 332. Like that. And that takes care of this chlorine and that one. And we've used this one. Okay. Now how about the other side? Rubidium chloride solid. Rubidium chloride solid right here. It's on the correct side. So if we put rubidium solid plus 1/2 chlorine gas yields rubidium chloride solid, okay, then we can use this value as is, minus 431 kilojoules. And that takes care of this one here and here. Okay. We have 2 left over. We need to cancel because we're not using this one or this one. And this one or this one. We've got these taken care of. We need to cancel the rest of them. So how about this one right here? Rubidium gas. If we put rubidium gas on this side, then it will cancel that one. And we need rubidium solid on this side. So do we need to change the sign of that one? Minus 85.8 kilojoules. And that will take out this one and here. And rubidium solid. Let's see if we can get rid of this chlorine gas. Let's see. Rubidium here. We've only got one more to go. So let's take out chlorine gas. Chlorine gas right here. Let's see. That was 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, that's right. We've used 4 of them. So we're going to do chlorine on this side. So this is 2 chlorine gas yields Cl2 gas. Right? Plus, we need to take half of it, right? Because we only need 1. So if we take half of that one, that leaves half of this one. And not only did we flip the equation, we took half of the value. So this is a negative 226 divided by 2. So that's a negative 113 kilojoules. Okay. Now let's see what happens. These cancel on opposite sides of the arrow. This one cancels, right, on opposite sides. This electron cancels that electron. And this rubidium solid is canceled by this rubidium solid. Okay. So cancel, cancel. Got this one, that one, cancel, cancel, cancel. This one here. We're good. So now we can just add up our value. All right. 397.5, change the sign. 332 plus, 431 minus, 85.8 minus, and 113 minus. So this is minus 695 kilojoules. All right. Okay. I think we got a couple more to go. 53. In spite of larger electronegativity differences between bonded atoms, beryllium chloride and has no dipole, while a sulfur dichloride does. So beryllium chloride has a dipole, sulfur dichloride does not have a dipole. So how can we explain that? We've got beryllium chloride, right? We drew the structure before. We have beryllium, Cl, like that, and like that. And maybe it's got a double bond on either side, maybe it doesn't. So this is a dipole that way and a dipole that way of equal strength. So this is no non-polar, right? We have polar bonds, but they're equal and opposite, so they cancel one another. While sulfur dichloride, sulfur has 6 and 2 times 7 is 14, so we have 20 electrons. Sulfur, chlorine, so that's 4 is 16. 2, 4, 6, 8, 10, 12. That leaves 4 more. So what we've got here is a tetrahedral structure with sulfur here and chlorine here, chlorine there, and in the back we have a lone pair, and on top we have a lone pair. So if we cover up those lone pairs, we have a bent molecule. And since the dipole is this way and this way for the bonds, but we have negatives in the other direction, I'm not sure which way. Probably the dipole is toward the back. But the explanation for the dipole is that you have polar bonds and lone pairs from a tetrahedral geometry that gives you a molecular geometry of a bent molecule. That means the overall dipole is the molecule is polar, whereas a linear structure gives you a nonpolar molecule. And so put that in your own words. And then we'll go on to 54. I believe that's the last one. Okay. We got going to do 3 things with this molecule. ICl4 minus. First, draw the Lewis structure. All right. So we have 5 halogens at 7 each, which is 35 plus 1. It's 36 electrons. Okay. So we put I, and then our chlorine. So that's 2, 4, 6, 8 is 28 electrons. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. That's 4 electrons. They have to go on the iodine. Okay. So what is the electronic structure? The electronic structure is octahedral, which means we have a square in the center with iodine in the middle. Then we have something here and something here. Now, in an octahedral arrangement, where do the lone pairs go? The lone pairs go here and here. And the chlorines go here, 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 and here. And what's more is that has a negative charge. So the lone pairs are at the apex. This is a nonpolar molecule. The shape of the molecule is square planar. This is electronic. This is molecular, square planar with that structure. And it's nonpolar. Okay. I believe that's it. Yep, that's it. All right, so this is Tuesday, the 15th of April, 2025. And we'll have an exam on this one Thursday. Yes, Thursday the 17th. And let's see, that's all we'll have on that day. So then the following Tuesday, we'll pick up with the last chapter, chapter 9, and that'll close out the semester.